Hi, good evening, everyone. I hope my voice is clearly audible. You can simply raise your hands to confirm this. All right, all right. Okay, so guys, we'll be waiting for a few more minutes, right? We are expecting a few more candidates to join in, right? So let's wait until 9:35 and then we'll start with our session. Hi, once again, good evening, everyone, and welcome back to the session. Right. So, in today's session, as we discussed in yesterday's session, I'll be walking you through the practical implementations of moments. Right. And the second part is I'll also walk you through the basics of inferential statistics, right, which is covariance and correlation. All right. And in addition to that, we'll also see lookup functions. All right. So let's begin. Right? So this is the same sheet we had been working since our day one. All right. So here in today's session, we'll see the practical implementation of moments, and we'll use the same data we had been working on. This is the employee data, right? And as discussed, that the moments can only be applied, or it is only defined for continuous data, which is why we'll filter out the continuous data from this data set and calculate their respective moments, right? So to figure out the first continuous variable that we have is the age column, right? The second is the annual salary column, right? And finally, we have the height column, right? Although is the also column, but it is a derived column, right? This was not the initially present in the data. Hence, what we'll do is I'll simply, let's say, hide it for the time being. And this is the column that we have. Right. So basically three columns all in total, right, on which we can apply the concept of moments. Right. Although don't worry, we'll also see this on another data set. So let's begin with this one. So here to calculate the moments, as I've told you, we already have functions defined, right? So you can check the same in the formulas bar here. Let's say if I'll go to formulas bar and more functions and the statistical functions. Right. So here you'll see a list of statistical functions. Those are available, and we'll be using the functions from this list only. Right. So for example, let's say the average is the mean of the data, right? Average if and average ifs is already done, right? These are, let's say chi-square test, etc. is part of hypothesis testing, right? We'll be using the correlation function, which is the correl function, right? Count blank, count ifs has been done. Covariance we'll be using today, right? And apart from that, we'll be using the variance functions here, right? After this, we'll also be using the standard deviation, right? So stdev function, right? And talking about the third moment is skewness, right? So we'll use the skew function, right? This is the skew function that gives us the skewness of the data, and followed by the same, we'll see kurtosis, which is the fourth moment here, right? So the name of the function is kurt. Yeah, here we are, right? So these are the four moments we'll be calculating, right? So let's begin. All right. So here, starting with, let's say the first moment, which is the mean of the data, right? We can directly use the average function. So this is the average function that returns the average of any given input. So in the input, we'll go back to function sheet, use the salary column, right? I'll close the bracket and hit enter. So this is the average salary of an employee in the organization, right? The same thing has we have already seen when we were discussing about a few functions, right? Here, right? The average function, right? So here, this is the mean salary of the employees within this organization, right? Talking about, right? So I'll just write the observation here that this is the average value of salary column. right? Moving on with the second moment, right? So this is your first moment, and this will be your second moment. So second moment is variance, right? And we have var function for that. Dot p is when you want to consider your data as population, right? And dot s when you want to consider your data as samples, right? So we'll always be treating our data sets as samples, and hence we'll use var dot s. I'll show you the output from var dot p as well, right? But we'll be using var dot s every time we want to calculate variance. All right, so I'll start with var dot s, right? And again, I'll pass the salary column. Right, so this is the column here, and this is the variance, right? So we are getting a very large value here, right? This value basically, we are getting such a large value because the total number of unique points or unique values that we have in our salary column is very high, right? So the total number of unique values that we have is already high, which is why we are getting such a high value as variance, right? And this tells you about the spread of the data. Let's say if we want to understand, right? If you want to understand, what I'll do is I'll plot a graph of the column, which is the salary column, right? And we'll be able to see what exactly this value indicates, right? So here, what we'll do is, let me plot a graph. And before that, let me mention that this is the measure of spread, right? So it tells you about the spread of the data, right? And let's see how this works. So I'll simply select my salary column. Right? I'll simply select my salary column and I'll simply plot it in the form of a graph, right? So you can go to insert column here and you see this chart section, right? In this chart section, there are a lot of various types of charts that you can plot here, right? So let's see what are the recommendations from Excel, right? So these are the recommendations. First is the line chart. You can plot a line chart out of the selected data, right? Next is the scatter plot that we have, right? So scatter plot is majorly used uh, when you want to compare two variables, right? But here we are only interested in one variable, right? Hence we'll not use this. Second is the histogram, right? It tells you basically within a given bracket of salary, how many number of people fall, right? And then we have this Pareto chart, right? So Pareto chart basically is a histogram along with the percentage. The yellow line that you see here is the total amount of data that is being covered at any given point here, right? So we'll be using histograms only. I'll explain you what this histogram is and how it works, right? So this is basically, let me set the chart title, right? So this is salary distribution, right? So this is basically the distribution of the salary. Let me, yeah, so this is the graph that we have. Right, so if you look at this graph here, yeah, right. So if you look at this graph here, right, this graph majorly indicates, let me, all right, sure. So this is basically, right here, this is basically a bracket of salary, and this basically displays how many total number of employees falls into that particular bracket. All right. So here we'll also see Okay, we are not interested in access titles. Yes, we are interested in data labels, right? So here, these numbers on top of each bucket of a histogram, this basically indicates how many number of employees fall into this particular bracket, right? Right, so let me see. Okay, right. So here, this is basically a distribution of the data. I'll explain you what this histogram tells you, right? So here, basically, we have a bracket of salary, right? This dot dot basically we have a number here, right? So since it's very large, which is why it's not representable, right? But this is a bracket of salary, and this is the, let's say, how it starts 40,063 to this will be up till 59,063, right? So this is one bracket, then 59,063 to 78,063 and so on, right? So this is how these brackets are divided, right? And each of these individual is called a bin, right? So this is a bin. So if we count how many total number of bins we have, this is the first bin, right? Let me change the color. Yeah, right. So this is the first bin. This is your second bin, third bin, fourth bin, fifth, sixth, seventh, eighth, ninth, 10th, 11th, and 12th, right? So there are basically 12 number of bins here in the data, right? And each of these bins represents a bracket of salary, right? For example, let's say the first bin represents the values are from 40,063 to 59,063. This is your first bin, right? And this particular value, 127, indicates that there are 127 employees whose salary fall into this bracket, right? And in the similar way, all other bins are constructed, right? Right? So these bins are constructed purely based on these brackets. The second bracket, I'll write the second bracket as well, 0632 78063. Right? This is the second bracket here, and these brackets, the total number of employees that work is 195 that fall into the salary bracket. All right, and so on and so forth. 187 is from 78,063 up till 97,063, right? So this is how these bins are constructed, right? And this particular, let's say if you want to know how this bracket is taken or why only this bracket is taken, so this is internally done by Excel, right? These calculations are done internally by Excel. So Excel has complete freedom of deciding the range, right? What range it has to split the data into. It's purely calculated by Excel. Although you can, let's say, if you want to modify this, you can modify it, right? Let's say, for example, right? For example, let's say there are two things that you can control in this particular graph, right? And these two things are, all right. So the first thing that you can control is the total number of bins that you want, right? So the range will be calculated internally, right? So range is calculated internally in this case. All right. So let's say if you want, instead of 12, I want 20 number of bins, right? So the range of values will be internally calculated by Excel in this case, right? The second thing that you can control is the difference between these two values, the difference between these two values, right? And the difference between these two values, let's say if I want, let's say bins with a difference of $1,000 or let's say $10,000, right? So based on this, the total number of bins will be calculated by Excel. All right. So let's say you can decide either the difference or you can decide the total number of bins, right? The other thing that will be calculated by Excel, right? If you decide the total number of bins, then the range will be calculated by Excel. If you decide the difference between these two values, right, then the total number of bins will be decided by Excel, right? So this is how histogram works. This is histogram. All right. And this histogram basically represents, or this histogram or any histogram in general, right, can represent one column at a time, right? And when one column at a time is calculated or displayed in the form of a graph, the other axis contains the frequency. This is the frequency column. All right. So this is how it's constructed. And the third thing is, if you want to, you can draw a kernel density estimation curve on top of histogram, right? All right. Okay, I see one of you asking why the difference is 19,000 only. I think this is the first thing that I've explained here. This difference is internally calculated by Excel. All right. This difference is internally calculated by Excel. All right. And these are the two things that you have control of, right? Either you can decide the total number of bins, or you can decide what difference or interval has to be taken between two values. All right. Okay. One of you is asking, why can't we change the difference? I've already told you, you can change this difference. Please focus, guys. Right. I've already told you, you can change the difference. Right. But how histograms are constructed, you should have equal difference. It's not like that. You'll have between these two values, you'll have the difference of 20,000. Right. So let's say for these two, for the first bucket here, you have the difference of 20,000, but in the second bucket, you only have the difference of 5,000. This cannot be done, right? This is not how histograms are constructed. This difference has to be same across the complete graph. Then only you'll be able to withdraw information from this. This difference, all of these difference has to be same. All right. Now, the third thing here is, right? So if this part is clear, I'll simply, remove this. Or let's say, okay, right. Now, the second thing is, right? So, why I subtracted, what exactly, right? You need to mention your doubt with a little more clarity. All right. Okay. So let's move ahead here. Right. Let me remove a few things. All right. So here, what we'll do is, right? So what we can do is, we'll be plotting the kernel density estimation curve, right? So this is kernel density estimation. Right? This kernel density estimation, it's a plot that will show you how your data is divided, or it basically shows you how your data is divided into various range of values. All right. So to construct a kernel density estimation on this, what we'll do is, we'll take the middle value, right? We'll take the middle value of every bin, right? We'll take the middle value of every bin here, and we'll connect all these middle values in the form of a line, right? So that it shows the pattern, right? So here I'll start with this value going on to here like this, and moving on ahead. Right? So this is how the yellow line that you see here, this is the kernel density estimation curve, KD plot, right? This shows you how your data is distributed, right? So data distribution across the variance, right? Or across the plot, and this plot basically shows you the variance. All right. So this is how your data is plotted. This graph will be more cleaner if we have higher number of bins, right? Instead of having 12 bins, let's say if I decide to have, let's say maybe 20 or 30 bins, this graph will take more clear shape, right? So let me show you. So here, what we'll do, right? We'll format the plot area here, and let's decide the total number of bins. All right, so here, this is the bin width that this is the first thing that you can control here, right? Instead of, let's say, taking 19,000, if I take a smaller value, I'll get a higher number of bins, right? Or you can decide the number of bins, right? Instead of 12, if you want a higher number of bin, that you can also do. All right. Now, so let's start with the first one, right? Here it's taking 18,202.9166, right? So what we'll do, we'll take the value of around, let's say 10,000. Right? So we'll take the value of 10,000 here, and let's see how is it changing. So this is how it is changing, right? We can see if we are getting higher number of bins. Yeah, so I think this is visible now. Right? So this is the range of values that we have. Right? Let me put this. Okay. So this is the total number of bins that we have, right? I think we can clearly see these values for the intervals, right? These values for the intervals. We can see this is the clear difference of 10,000, right? And this is across all the columns here, or let's say all total number of bins here. The difference is 10,000 for each of it, right? Going up till the last one. right? So we can see the total number of bins has been increased, right? So now this is 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16, 17, 18, 19, 20, 21, and 22, right? So these are the total number of bins that we have. 22, right? Now, if you take the middle point of every value here, right, you'll get a plot like this, right? So this is taking more detailed shape, and this will help you to analyze the pattern of values in this data, right? Like this, right? So this is basically the KDE plot that we are talking about, right? You can increase the total number of bins further, and you'll be able to get more detailed plot, right? So let's do that. So what I'll do is I'll format the plot area, right, to the right. So here we can change, let's say, instead of deciding the bin width, we'll decide the total number of bins, right? So instead of 22, let's say if I take 50 number of bins, right? And let's see. So this is how the plot has changed, right? And we can see more detailed plot now, right? If you connect the dots again, right? If you connect these dots, you'll see a more detailed pattern of how the data is distributed across different, let's say, range of values in this data, right? So like this, you can see this is the plot, right? So this is exactly how you can analyze, and you'll be able to see how many, if you are, if you look at this data very closely, you'll see, let's say if I decide up till this value, right, up till this value, majority of people are falling in left side of this, which means this organization, in this organization, there are more employees who are earning less than, let's say, this particular value, less than 131,806, right? Whose salary is less than 131,806. All right. And there are less number of employees, right? Less number of employees whose salary is very high, whose salary is very high, right? If you, let's say, the total count of employees is 1,000. If we see, almost 70% of the employees falls into this range or the left side of this. Right. So yes, after changing the bin number or number of bins, the range of the bin will automatically be adjusted. All right. So yes, this is how your KDE plot looks, and it tells you about the distribution of the data, right? The ideal distribution that we talk about, right? The ideal distribution that we talk about, your data should be normally distributed, which means the distribution of the data should be something similar to this plot. It's called the bell-shaped curve, right? It's a bell-shaped curve, and the plot, or let's say the distribution of your data should be like this, right? And this bell-shaped curve, if it comes with, let's say, if the center value here, and these are the, let's say, one standard deviation to the left and one standard deviation to the right. Right? If all of your data falls into one standard deviation, right? Let's say 97% of the data, not all of it, but yes, 97% of the data. This is a rough figure, right? And let's say if we extend the tails on both the sides, we'll see that within two standard deviations, right? Within two standard deviations, 99% of your data falls, right? And within three standard deviations, 100% of your data falls within three standard deviations, right? So if this bell-shaped curve have these properties, then it is said a normal distribution. Right? And this normal distribution is basically a type of distribution in statistics. All of your, let's say, any data that you're passing as an input, any data that you're passing as an input in your machine learning algorithm, right? If you're passing any input, or let's say any input in machine learning algorithm, so this input is basically, we are talking about data, right? You pass data in your machine learning algorithm, right? And this data should follow normal distribution. This is one of the prerequisites of machine learning algorithms. If your data follows this normal distribution, your machine learning algorithm will be able to train itself using this data at its best. Right? So this normal distribution is basically a bell-shaped curve with this particular property, right? This property you learn in z-score, right? The z-score is very similar to, or z-score is basically the statistics behind this distribution, which is called the normal distribution, right? You'll study this z-score in machine learning, and this z-score is basically the score that tells you how much data falls into first, second, and third standard deviation. All right. And the shape of the data should be like this. As of now, if you see on the salary data, right, the shape of the curve is very different from this particular shape. Right. So in the pre-processing part, what we do is we'll convert whatever distribution of data we have into normal distribution. Right. And this is a very long and lengthy process. It needs a lot of analysis while you're transforming the distribution of the data to normal distribution. All right. So this is basically one of the major reasons why we study histogram, right? Because on top of histogram, KD plot is plotted, right? And this KD plot will tell you about the distribution of your data, right? And by simply visualizing this distribution, you can have an idea whether your data is following normal distribution or not, right? So if it is not following normal distribution, we need to carry out pre-processing while preparing the data for machine learning algorithms, right? And this stands as one of the most important and crucial step through the complete machine learning pipeline, right? Because there are a lot of things that you have to keep in mind when you're converting your data to normal distributions. What exactly are these things? You'll study in your machine learning days. Right, so I hope this part is clear to everyone. Histogram, kernel density estimation, and the normal distribution. You can simply raise your hands to confirm this. Else, if you have any doubts, you're free to ask in the chat section. Right, so guys, we'll take a 5 minutes break and then we'll proceed ahead with further discussions. Right, so 5 minutes break. All right, so let's begin, guys. All right, so this is your salary distribution. Okay, one of you here is asking why increasing here the number of bins so that we can see how the employees are distributed along various salary ranges, right? These are the range of salaries, and this is the total number of employees that are falling into this salary bracket. All right, now moving on. Right, moving on, we'll also see since we have checked the variance, we'll also check the standard deviation, right? Because it is nothing but it is simply the square root of variance, right? So I'll simply see the standard deviation, right? And we directly have std dot s function here, right? For samples dot p for population, right? So we'll see, and we can directly calculate this on salary column, right? And this is the standard deviation. All right, and this is basically how far your data point is from the mean of the data, right? Let's say how far from the mean, right? So how far from the mean basically tells you about the deviation, right? How deviated it is from the mean, right? Hence called the standard deviation. All right, and this is again, if you take the square root of variance, right, you'll eventually get the same value. All right, so this is how the standard deviation is defined. Moving on with the third variance, right? Third variance basically tells you about the skewness, right? And skewness, we directly have the dot skew function, right? It returns the skewness of the data. We'll pass the salary column again. And this is the skewness 0.88, right? So the skewness basically tells you about the biasedness, right? And biasness in what form? Biasness, it basically tells you in simple terms how far the distribution of the data is from the normal distribution, right? The current distribution of your data, how far is it from normal distribution? This value tells you about that thing, right? And if you see the distribution of this data, this is very close to normal distribution, but the biasness is towards the left values or the lower values, right? If you look at the left side of this graph, right, left half of the graph, you'll see that there are very high number of employees falling into the left side of the graph. Hence, it is biased towards the lower values, right? Lower values of the salary, of course. All right, so this is what skewness tells you. And moving on with the fourth moment, we have the kurtosis, right? And we directly have the kurt function. Can directly use the salary column here. And this is the kurtosis that we have, negative of 0.04, very small value, right? And this tells you how high or low the peak of the curve is, right? When we see or when we consider normal distributions, as you see, it's a bell-shaped curve, right? So the top or the highest point of this curve, how high it is, this value tells you about this, right? The value of kurtosis. Hence, the measure of peakedness, right? How high the peak of the curve is or how low the peak of the curve is, right? From normal distribution. All right, and just to give you this idea, let's say for normal distributions, there are a few properties associated for normal distributions. And the first property is it should be bell-shaped curve, right? The second property is 100% of your data falls in within 3 standard deviation. Right? within 3 standard deviation, 97% of the data falls within 2 standard deviations, right? Sorry, within 1 standard deviation, right? And 99% of the data falls within 2 standard deviation, right? These are a few properties. Additionally, the skewness of this data is equals to 0, right? The skewness for a normal distributed curve is 0, right? So yes, you can also get negative values for skewness, right? If the dominance of the values, right? If the higher values are present on the right side of the graph, right? Higher values in terms of frequency, right? If this is present on the right side of the graph, you'll get a negative value for skewness, right? Since these are present on the left side of the graph or left half of the graph, which is why you're getting a positive value, right? Since we are getting a positive value, it's called positively skewed. If you get a negative value, you can say it is a negatively skewed data. Right? So this is positively skewed data. Right? So right? So this is a positively skewed data. All right. So these are basically the moments, right? These are the moments that we have discussed, right? And the respective observations that we can extract from this analysis of moments, right? Now, if you see, we also have a direct function for descriptive statistics, right? You can go to your data tab here, right? And you see the data analysis tab, all right? So what we'll do is we'll perform a basic descriptive statistics on the data, right? So I'll go to my data analysis tab here, right? And this analysis tab, basically we have various kinds of statistical analysis that you can do on the data, right? Sampling, regression, rank and percentile, right? Random number generation, t-test, one pair, two pair, Fourier analysis, right? Exponential smoothing, descriptive statistics, correlation, covariance, etc. ANOVA test, right? So we'll do the descriptive statistics, right? Since we have been studying descriptive statistics for quite number of days now, right? So let's see what exactly this descriptive statistics tells us about the data, right? It will pick the continuous data from this column or from this complete data set, right? And give you few descriptions of the data. For example, let's say what is the mean of the data, right? The second thing is percentiles, the minimum value, maximum value, how many records are present. This kind of information it will provide you, right? So let's see. We'll click OK after selecting descriptive statistics. I want the output in, okay, new worksheet, right? And let's say this is the input range that I have to select. So after clicking on this, I'll select my complete data, right? So A22 P1001, this is my data. And what all output you are looking for? Summary statistics, right? I want the confidence level as well, kth largest and kth smallest. So this is first largest and first smallest, hence the minimum and maximum values, right? And let's click OK. Okay, so let's do that on the salary column, right? Let's do that on the salary column. Let's click OK, right? So this is the output that we are getting. Let's see what this output basically represents. All right. So this is the output that we have got from when we have applied the descriptive statistics, right? So this is basically the descriptive statistics that we have calculated. All right. Now in the output, you're getting mean of the data. This is the mean value of the salary column, right? This is the standard error. This is the amount of error that you can get on this mean value, right? So you can say mean plus minus the standard error. All right. Next is the median of the data. This is the middle value in the sorted data, right? Next is the mode. Mode basically represents the highest number of employees drawing the same amount of salary, right? So that salary is 70,165, right? So maximum number of employees are drawing 70,165 as their salaries. If you really want to see what exactly is the total number of count, we can simply apply a filter on 70,000, right? I'll unselect everything and I'll only select right? So I think it is 165, right? So we can see there are the total number of employees is 2 who is drawing this value of salary, right? Apart from this, no two employees within this organization have same salary figure, right? There's some or the other difference, right? The salary figure is not exactly same. All right. Next is the standard deviation, right? This is the standard deviation of the data, how far data points are on an average from the mean of the data, right? Next is the sample variance. This is the variance of the sample data, or let's say considering your data as a sample, variance has been calculated, right? Next is the kurtosis. This is of course the fourth moment of the data and followed by skewness, right? Next is the range of values, right? So this is the range that is calculated using maximum minus minimum, right? This is the minimum value and this is the maximum value. All right. Followed by this is the sum of all these salary figures. You can say this is the budget of salary for this organization. All right. Although it is also included of a few employees, those who have left the organization, right? The total number of count of employees is 1,000. All right. This is the first largest and first smallest value. And this is the confidence interval. All right. So yes, this is the descriptive statistics that we are getting. All right. So I hope this part is clear to everyone. You can simply raise your hands to confirm this. Right. Okay. Confidence interval. See, basically in statistics, whenever I'm doing any kind of calculations, right, I should have, let's say there's always a margin of error, right? Especially in statistics, whenever you are doing any calculations, there's a margin of error. And this is the standard error that we have, right? In everything that we are calculating, there is a confidence level or the confidence interval that is involved, right? And what this confidence interval value tells us is how much, let's say, the output that you have got, which is up till these values, right? How much is how much, let's say, the amount of confidence is, all right? And this value that we are getting as the output, it indicates the total confidence level. When the confidence level is 95, right? When the confidence level is 95, what exactly is the respective values that we are getting? This is the measure of this confidence. All right. Okay. One if is asking why we are learning these things when it is present on a single click. You're basically learning this because all of these will be used in data analysis and in machine learning, right? Without analyzing the data mathematically, you cannot pass the data into any mathematical algorithm, right? Which is why you need to understand all of these values that you're getting and what exactly they represent, right? Based on this only, you'll be, building your strategies, how to analyze data, and you'll also, let's say, take decisions for the machine learning projects. All right. So all type of analysis has to be done on the data to understand it in a better way. All right. And understanding the data statistically is one of the best approaches to gain insights or the hidden information from the data. All right. The next question is, do we have to remember these formulas? Don't worry, as and when you'll be using these concepts, these formulas will be on the tip of your fingers, right? So you don't have to, let's say, memorize, but yes, as and when you practice, right? So you have to practice as much as possible, all right? At least give 2 hours of practice on daily basis. This will help you to build your skills. All right, and data can be taken from Kaggle. I think I've already explained the platform of Kaggle, right? I've also uploaded one document on your GitHub link that I've shared in previous days, right? I've shared 2 datasets. One is the data of accidents, right? And the second data is related to the different types of crimes taking place across various districts in India, right? And this is present for the year of 2014, which is 2014, right? So you can analyze that data and try to, gain some insights out of it, right? Try to extract some valuable information that you can use or that you can pass to decision makers, which will help them to improve their decision. All right. Now, moving on. All right. So here, moving on, we'll also discuss about the inferential statistics that will tell me about the relationship between data, right? So just to give you this idea, let me show you the data that I've shared with everyone. Right. So let's say this is the data that we have, right? The total number of records that we are having. All right. So this is for the year of 2023. If you look at the total number of districts that we have, right? So let me format this as a table first, right? We'll get a lot of features to add on. Yeah. Right. So this is the data. And if you look at this data set majorly contains the various types of crimes into various districts, right? Within various states in India, right? And so this is a very valuable data, and you can extract a lot of insights out of this. right? So these are a few things that you can analyze, right? The total number of columns in this data is very large. We have around, I think, okay, so this is somewhere around uh, 40 columns, right? And try to, take this as a homework and try to extract the insights from this, right? We'll be using this data in one of explaining one of other concepts as well, right? And that concept is correlation. All right. So here, what we do is there are two things, those are associated, right? So the next part here that we are discussing is part of inferential statistics. All right. And this is the basics of inferential statistics that we are discussing for today. So, right, we'll be discussing about covariance and correlation. Right. So these are the two topics that we'll be discussing. All right. So let's pick covariance and begin with the discussions. All right. So this covariance here is majorly, co stands for combined, right? And variance we have already studied that it tells us about the spread of the data, right? So this covariance majorly means combined spread, all right? And combined spread. So since, you know, a combination has to be made. So this combination will be of two columns, right? Because spread or the variance can be calculated on continuous data, right? It can be calculated on continuous data only. And if we calculate or if we want to understand the common spread, right? If we understand or if we try to understand common spread between two columns, right? And these columns will again be continuous in nature, right? So if we have two such columns, we can analyze how they are varying or how common spread they are sharing with each other, right? And this value of covariance you can get from negative infinity to a positive infinity, right? Which means any value across the number line you can get, right? And covariance, what it tells you about the common spread of the data. All right, so you can directly use covariance to understand the common spread, right? Or combined variance, which is basically a kind of a relation we are analyzing, right? So this is basically the relationship measure, and this relationship measure is termed as covariance, right? And since it is telling us about the relationship, how two columns are related with each other, this is the information your covariance gives us, right? But there's a catch here, and the catch is, all right, so before, let's say, understanding the catch, let me give you the formula for covariance, right? So if you recall the formula for variance, right? So the formula for variance is summation of xi minus mean of the data, square of it, and divided by the total number of elements minus 1, right? This is the variance, and this is for a single column, right? This is for a single column. Now here, since in covariance, two columns are involved, right? Hence, we'll have to distribute this particular formula into two different columns, right? And how this can be done is, let's say if I take the formula here, I can write the square as 2 times. For example, let's say if I write the square of 2 like this, or I can write it like this, 2 multiplied with 2, right? So what we'll do is we'll write the formula like this. This way you'll be able to understand things with more clarity, right? So this is xi minus x bar, which is mean of the data, multiplied by xi minus x bar, right? So this is just nothing but we are expanding the formula here, right? And this expansion will help you to understand how eventually we are able to get the formula for covariance. All right. Now, the second thing is, since 2 columns are involved, right? So what I'll do is the 2 values that I have here, this is my first value and this is my second value, right? So these 2 values that I have here, I'll simply use these 2 values for 2 different columns, right? So I'll replace, let's say, let x represents 1 column values, and let us use some other variable for representation of other column values, right? So let's say if this is the first column and this is the second column, I'll simply use a representation of y instead of x, right? So how this can be rewritten is summation of xi minus x bar. This is for the first column, right? Multiplied with yi minus y bar, right? This is for the second column. And I'll divide this by the total number of elements minus 1, because the total number of elements will remain same in this, right? Because the total number of observation is same. Let's say if I pick high column and if I pick salary column, the total number of values those are present in these respective columns are exactly same, right? Which is why n remains as it is. All right. So this is basically the formula for covariance, right? This is the formula for covariance. And this is how covariance is calculated mathematically, right? So here, no, since this is the formula, right? Here is a catch with covariance. Right. So before, let's say, seeing the catch, let's calculate the covariance on a given column so that we'll be able to understand this in a better way. Let me share the same Excel spreadsheet we were discussing earlier. Right. And let's say this is the functions column. Correct. So this is the original data, right? And let's calculate the covariance, right? Let's analyze the covariance and what exactly it tells us, right? So here, let's say, since we are having the employee data set, right? So we can simply use, maybe if you can understand, right? The salary of an employee is dependent on a lot of things. And what exactly are these things? Let's say which department, right? Let's say what is the age of the employee? What is the total number of years of experience employee has, right? There are a lot of things. Let's say the skill set employee has, right? On these factors, the salary of the employee depends, right? And this is the real case scenario whenever, let's say, a salary is projected, right? So this is dependent on, or the calculation of this salary figure is done based on a lot of things, right? So let's take years of experience. You'll be able to understand this or relate this in a better way. Let's pick these 2 columns, right? So salary and the years of experience. So here, if I want to analyze, right, what is the dependency of salary on years of experience, right? So I want to analyze some kind of relationship between this, right? Basically, I'm trying to analyze some kind of a relationship, right? I should be able to know how these two columns are exactly related to each other. Whether, let's say, if the years of experience increases, right? If the years of experience increases, the salary also increases, or if years of experience increases, the salary decreases, right? How will I judge this? Right? So I'll judge this based on the covariance value. I'll analyze the variance or the spread of these two columns, and how commonly they are sharing the spread tells us the value of covariance. All right. This tells us about the value of covariance, and hence, if covariance is a negative value, right, this basically means the two columns that I have selected, they are indirectly proportional to each other. Right? Indirectly proportional basically means it is represented like this. Let's say if I want to represent salary and experience with a negative correlation, I can represent it like this, that the years of experience is inversely proportional to the salary of the column, right? This basically means if the experience increases, right, the salary will decrease, right? This is the first scenario. The second scenario is you can get a positive value, right? You can get a positive value for this. And positive value basically indicates that both of them are directly related to each other. Or let's say directly proportional, right? Since this is more technical term, you need to, use technical terms as and when they are to be used. Right? And this positive relation can be represented like this. Salary is directly proportional to the years of experience. And this basically says if the value, or let's say if the years of experience increases, the salary increases, right? And vice versa. If the salary increases, the years of experience increases, right? Although, let's say in this particular case, this scenario is not fitting properly with logic, right? Someone is having higher salary does not mean he's having higher number of years of experience, right? But yes, vice versa is true. If someone is having higher number of years of experience, he is expected to ask for or demand for a higher salary, right? So this is how it's related with each other, right? And if years of experience increases, salary also increases. This basically is the direct relationship, right? And this is positive covariance. Right? And this particular scenario where number of years of experience increases and the salary decreases, this is an indirect relationship, and this is represented using a negative value of covariance. Right? Now, here is a catch. And the catch is, let's say, usually what happens, right? Usually what happens in the data is, let's say, try to understand one thing. If this part is clear, I'll, let's say, erase this part. You can simply raise your hands to confirm this. All right. Right. So here, there's a catch with covariance, and that catch is, right, the catch is for covariance. The catch is in the formula itself. If you look at the formula for covariance, it's written like this: covariance between x and y is written like this: summation of xi minus x bar multiplied by yi minus y bar, right? And this will be divided by the total number of elements minus 1. All right, so this is the formula for covariance. And if you look at this formula, values are involved, right? These values are involved here. Xi's, these are the values. Yi's, these are the values from the data itself. All right, so when we'll be defining covariance, right? When we'll be defining covariance, we'll also will always see the direct or indirect relationship, whether two features have direct versus indirect relationship, right? Both of them are directly proportional to each other or inversely proportional to each other. All right. And since these consume individual columns values, right? Which is why in data, one thing happens, let's say, for example, two columns we have here, right? So this is one, maybe two, three, four, five, six, like this, right? Now, what happens is when I analyze the relationship between these two columns, right? If I'm analyzing the relationship between these two columns, let's say I get some covariance value, right? Between X and Y, I'm getting some value here, right? A number, right? Now here, what I'll do is, let's say I'll modify this data to X square and Y square, like this, right? So how the values will change? The square of one is 1, the square of 2 is 4, 3 is 9, 4 is 16, 5 is 25, and 6 is 36. All right, so these are X squares. Let's represent them with as X dash, Y dash, right? These are the square of original values, X dash and Y dash. Now here, if I analyze the covariance again for X dash and Y dash, right? It should be exactly equals to the covariance, because this is covariance of X and Y, because it is representing a relationship, right? These values are representing a relationship, and relationship between data points do not change if you change the physical value of that particular data, since we are talking about a series of data, right? Or a range of data. So this series of data or a range of data, right? The series of data or a range of data, we're not talking about one value. We are talking about thousands of values or millions of values at once, right? And when there's a relationship between these features, right? When there's a relationship between these features, this relationship has to be, is expected not to change, even if I'm applying same kind of operation on this both the columns, which means, let's say if I add any particular value to every element of the both the columns, the relationship will not change, right? But here, in case of covariance, this relationship changes because it is highly dependent on the values of the data. These are the values for column X, and these are the values for column Y, right? And the calculation of covariance is heavily dependent on the values present or the elements present, right? Which is why if these values are squared, the value of the original covariance changes. It will get higher because there is a higher number that we are having here, right? This is one of the reasons why covariance is not used, or we can say that it is not reliable, right? Because we are making all the decisions based on some or the other kind of quantification. We are trying to display everything as a number in statistics, and I can only trust on reliable resources. I cannot trust on something that is expected to change where it should not change, right? Which is why we have a variation of covariance called correlation, right? This is the variation of covariance, which is correlation. This can be said as standardized covariance. Standardized covariance. All right. Now, to see this, I hope this covariance part is clear. Why it is not reliable? You can raise your hands if you are able to understand why covariance is not reliable when we are dealing with statistics. All right. And okay, guys, I see, you know, very less, let's say, involvement, right? It's very less involvement. I hope everyone is able to, you are able to understand what we are discussing in these sessions. I can understand that from yesterday onwards, the sessions are being more technical, right? But these are a few things that you have to understand, because without these, journey in your machine learning will be very tough, right? Because all of these things are used in machine learning. Although as and when it is required, the new topics will are covered from scratch, right? So these are a little technical things, which is why I had already suggested you some reference books, right? If you're finding it difficult to understand any particular term, right, you can simply check the reference book and you'll be able to get it. Right? Okay, guys, I can see. Okay. I can see. Okay, I'll just give you a recap of why covariance is not reliable. Right? Just look at the formula for this. All right. So here, I hope everyone is able to understand that these xi's that we have here, xi's and yi's, these are data points from x and y column respectively, right? You can raise your hands if you are able to understand this, that xi's and yi's are taken from the columns itself. It holds the values of the elements in the column, right? So since these holds the values of the in the column, let's say these values are 1, 3, 5 for x and 2, 4, and 6 for y. All right. Now here, what happens is, since covariance, this is representing a relationship. It is representing a relationship between the columns. How it is varying, how two columns are varying with each other, right? This is the combined variance as right. This value is the combined variance that we are getting, right? Because it involves combination of two columns, right? So here, what happens is, since these values are being consumed in the calculation of covariance, what will happen is, let's say if I multiply both of these columns with the same value, right? Let's say I multiply both the columns with 2. I'll do 2 times both the columns, right? So x dash will become 2 times of 1 is 2, right? 2 times of 3 is 6, and 2 times of 5 is 10. These are the new values. For y dash, we'll see that multiplying 2 with 2 is 4, 4 with 2 is 8, and 6 with 2 is 12. So these are the values now. Now, if you see, right, for original covariance between x and y, let's say we have some value here. Let's say v1, this is the value, right? And for covariance with x dash and y dash, this is v2. Ideally, since it is representing a relationship, my v1 should be equals to v2, right? Because it is a relationship, it should not change if I'm making same changes in both the columns. right? You understand it like this. For example, let's say there are two people who are friends, right? These are two people who are friends. Let's say this is person one and this is person two, right? Person one and person two are friends with each other, right? These are friends. Now, these people individually, they have their body dimensions, right? The length of leg, or let's say the length of waist, and so on, right? The body measurements basically, right? So let's say this person has a chest of 40, right? This person has a chest of 42, right? So here you understand, since these two are friends and this friend is a kind of relationship they are sharing with each other, right? So let's say 20 years down the line, person one, with age gets little fattier and the new chest size is 44. All right. And this person too also gets older with time and his new chest size is 46. Right. So here, since the body dimensions have changed, this does not mean that the relationship will change. Right. P1 and P2 will still be friends down the line. Right. They'll be friends down the line. Just because the body dimension has changed will not change the relationship between these two people. Right? This is exactly replicated here. Since these covariants, these are representing a kind of relationship between columns, it is not expected to change if I'm applying the same operation on the data for both the columns. Right? So this is one of the major reasons, but this covariance in actual, it changes, right? This V1 will not be equals to V2, right? This is the real scenario and this is the ideal scenario. Now, the real scenario is not matching up with the ideal scenario. Hence, this is not reliable. It's not reliable. Although we can calculate covariance, right? But still, it is not reliable because its value will change if I apply some kind of operation on my data, right? The data transformation, if you remember, data transformation that we were talking about to remove skewness from the data, right? The data transformation that we were talking about in yesterday's session, this transformation is used, right? So these transformations are applied across the data, right? Across the data so that skewness will be brought to zero, right? And in this operation, what I'm doing is I'm changing the values of the column. If you remember, I also told you that data scaling is one of the common process where we simply scale the data using either standardization or normalization, right? So here also we are applying same operation on both the columns, right? And since just because the values are changing should not change the relationship between these two columns, all right? And in reality, in covariance, these values changes, which is why it is not reliable, right? Because it is not showing the same amount of relationship, right? This value will increase, covariance value will increase, right? And since in statistics, I'm highly dependent on quantization, right? So this quantization process or quantification process is not reliable. We have to make some modification on this so that it becomes reliable, so that I can trust this value, right? Because on these values, I'll be taking a few of the majority decisions to analyze my data. All right. So this is one of the major reasons why an advancement on this is done and we standardize this covariance. We'll simply standardize the covariance so that once it's divided by the standard deviation, right? Standardizing basically means dividing by standard deviation. We have seen this in yesterday's session as well, right? For every moment, let's say not every, but yes, for the third and the fourth moment, the process of standardization is done, right? So that values do not change if the data is changing. right? So talking about the standardization of covariance, I'll rub this part and we'll see the standardization of covariance. I'll write the formula first for covariance itself, right? This is covariance between two columns, x and y, will be summation of xi minus x bar multiplied by yi minus y bar, right? And this will be divided by the total number of elements minus 1. This is the formula for covariance, right? I'll standardize this. Here, what I'll do is I'll standardize this formula, and the new formula becomes summation of xi minus x bar, right? Yi minus y bar. This part will remain same. The total number of values will remain same, which means n minus 1 in the denominator remains same, right? The only adjustment that will be done on this is I'll simply divide it by the standard deviation of x and the standard deviation of y, right? So this has been standardized, and the standardized covariance is called as correlation, right? This gives you correlation. It is represented with small r, right? So the covariance formula, the correlation formula is the standardized formula of covariance, right? And since covariance, we have standardized the formula, which is why what will happen is these relationship values will not change if I change the values or apply the same operation on both the columns, right? Taking the same example of x and y, right, with 1, 2, 3, 4, 5, 6 as the values, and x dash and y dash, where we have multiplied both the values. So this is 2, 4, 6, 8, 10, and 12, right? So these two values will remain as it is, right? For both of them, let's say this is COV1, this is COV2, respective covariances, and let's say R1 for correlation for the first one and R2 for the correlation of the second part or the second form of data, where let's say you can say some kind of transformation has been applied, right? So this can be termed as data transformation. I've applied some transformation across the data, and hence the values have changed, right? So for these, covariance will not be equal for both the data, but yes, correlation will be equal for both the data. Hence, this becomes a reliable resource, right? It becomes a reliable statistic that I can use to make some decisions. All right. So here, since this is standardized, and once you standardize anything, the values are from -1 to +1, right? Which is within one standard deviation, right? So since these are standardized, this will be within one standard deviation, these values of correlation. Hence, the range of correlation is from -1 to +1. The range of covariance is from -infinity to +infinity, right? And again, the same logic is applied if you're getting a negative value for correlation, right? This is inverse relationship. And if you're getting a positive value for correlation, this is a direct relationship. And on top of it, the value that you're getting for correlation, let's say you're getting some R is equal to 0.5, right? So this is the strength of relationship between X and Y, right? This is the strength of relationship between X and Y, right? So this is how we analyze our data. We can find the correlation between, let's say, taking the same employee data set, I can find the correlation between, let's say, salary and maybe the years of experience, right? This will be one correlation. So let's represent this with R1, right? And let's say we find another correlation, R2, and let's say this value is 0.5, right? And let's say some other correlation between salary and maybe age, right? You get some other value, maybe 0.2, right? So what I can say is salary has the calculation of salary will be when the calculation of salary will be done, right? The years of experience will have more weightage than the age of the person. Let's say if some person is 50 years of age and haven't worked until he's 50, right? So the age is higher, but he do not carry any experience. All right. And this is how these correlation values will help you to make decisions, right? Which is more important feature while calculating any output or any other value, right? So in this case, when we are calculating salary, I want to see whether salary has more dependency on the number of years of experience and versus whether the salary has more dependency on the age of a person, right? So here we found out that it is 0.5 and 0.2 respectively. Hence, 0.5 has more weightage, right? Since this is a higher value. So hence this has more weightage, which is why when I'll be calculating the salary, the years of experience plays a very important role than age, right? You can also find, let's say, year. You can also find, me let's say, write down here, right? You can also find some other value R3, which will be the relationship between salary, right, and the mobile number of the person, right? You'll see this value very close to zero, let's say 0.01, right? This shows no relationship. Any value that is close to zero, right, is can be considered as zero itself, right? And this, if any correlation value is coming out to be zero, the columns that you're using to calculate the correlation, they are not dependent on each other, right? They are independent of each other, right? So this is how you can analyze the correlation, covariance, etc. Right? So for this, what happens is, let's say if you have a very large number of columns, right? If you have a very large number of columns and you cannot manually calculate correlation and covariance every time. So what we do is we calculate covariance and correlation in the form of a matrix, right? So for example, let's say if I want to find like this for X and Y, I'll write X and Y here and X and Y here, right? So here, this particular value, let's say V1, this value represents the correlation between X and X. V2, this represents the correlation between X and Y. V3, this represents the correlation between X and Y. And V4, this represents the correlation between Y and Y, right? So always remember the correlation between same columns. For example, if you go on calculating correlation, some R4 between salary and salary itself, there will be 100% correlation. Hence, you'll get the value as 1. Between same column, if you're taking, instead of both the columns, you're taking the same column. And if you're trying to calculate covariance here, you'll get the output as 1, right? Because this is the common variance that we are calculating. And if you get the value of covariance as 1, right? Sorry, not the covariance, but the correlation. You'll get the correlation value as 1. Right? And once you get the correlation value as 1, these are fully dependent on each other. Fully dependent on each other. Right? You can say if the value in salary column increases, the value in salary column increases. This is how I can take the observation. Right? So for example, let's say if we talk about the correlation R1, salary versus experience, if the number of years of experience increases, the salary increases. This goes vice versa as well. If the number of years of experience decreases, the salary also decreases, right? So this is how you can analyze this, and this is how you can spot the columns that have more importance while calculating any of the features, right? In prediction, when you'll be making predictions in machine learning, you have to select one column as the target variable. This target is basically the column that you'll predict, right? So let's say if I want to make prediction of the salary based on numbers of years of experience, age, mobile number, gender, department, ethnicity, etc., age, and so on. So I can combine, I can simply pass all of these columns and make prediction of the salary, right? Once the machine learning model is trained. All right. So this is how these correlation and covariance majorly work. All right. So let me quickly show you how values can be calculated. All right. So here, what I'll do is I'll calculate the covariance. Covariance can be calculated using the covariance formula, right? Covariance.s, of course, considering our data as samples. I'll have to pass two arrays here, right? Two arrays are basically two columns on which I want to calculate the covariance, right? So let's calculate the covariance between maybe the age column and the salary column, right? So I'll select one of the columns as age, followed by a comma. I'll select another column as salary, right? I'll close this bracket and let me show you the formula, and this is the output, right? So this is the covariance that we have calculated, right? This is covariance, all right? And let's see what is the correlation. So as you can see covariance is basically a negative number, which basically means as the value in my age column increases, the salary decreases, right? If you see a scatter plot between age and salary column, you'll easily be able to identify this difference, that as the age increases, the salary of the person is decreasing, right? This basically means this particular organization has younger people who are having high amount of salary, right? I'll repeat this. The observation that I'm taking from this output, right, which is a very high value of covariance, and that too negative correlation uh, on inverse proportion, right? So here, let's say the observation that I'm taking is, if I go according to the definition of covariance, I'm getting a negative value, which means if value in one column increases, the value in other column decreases, right? So I can simply write age increases, salary decreases. This is the mathematical, this is the observation based on how the definition is written, all right? If one column increases, the other column decreases, all right? Now, if I analyze this statement, because this statement is true according to the definition of covariance, right? And now, if I write the human interpretation of this, I'll be writing that, let's say, people with less age are making more salary, or let's say they're drawing more salary from the organization, right? And the people with high age, they have comparatively less salary, all right? And same goes with correlation. This is a standardized covariance, will be, we can easily calculate using Correl function, which is CORREL, short form of correlation, right? And let's say I'll again use same two columns here, salary and annual salary and age. I can see this value is very close to zero. If I see the standardized form of this, right, since my value of covariance is not reliable, right, it is expected to change if I apply any kind of transformation to the data, right? But my correlation value will not change, right? And this is a very small value. Negative of 0.02 is very close to zero, right? Hence, based on this, I can say there is no relationship between age and salary, right? And out of these, the statement written against correlation will be accepted, because correlation is a reliable resource of statistics, but covariance is not. right? Which is why this is giving us more clear information or more clear insight about this data than covariance. All right, so this is how it's calculated if you want to calculate it manually, right? So for example, let's say if I have, let's assume if I'm working with a data that contains 100 columns and I want to see the relationship between every two columns, right? So for that, I have to, write, if I go on calculating this manually, there will be a lot of time that is going to be consumed, and there are a lot of, let's say, resources that will be consumed, right? So for that, these are a very generic process in the data analysis, which is why we directly have features that will avail us with the features of analyzing all the columns at once, right? So covariance, correlation, all of these can be analyzed with a single click, right? In Python as well, you have functions defined for it. You can directly plot a correlation matrix that will represent the relationship between every two columns in your data, right? So certainly in this particular data, we do not have, all the categorical columns, right? But yes, the data that I've shown you, which is the district-wise crime data, this data set has all the columns which are numerical in nature, or I can say which are continuous in nature, right? So what we'll do is we'll calculate the covariance matrix on this column or on this data. Right? Okay, one of you is asking, since the covariance is not reliable, what it is used for, right? So covariance forms the foundation of correlation, right? Which is why covariance is important to learn. Apart from this, there are some algorithms in machine learning that uses covariance, because if you are able to absorb the common variance from the data, right, you're free to drop the column itself, right? You'll learn about this. There's a process of dimensionality reduction in machine learning, right? And this dimensionality reduction is done when you're dealing with a very large scale of data, right? When your data has very high number of columns. Let's say if you're working with a data that has 1000 columns, right? So basically the total number of columns your data has, that is the total number of dimension of data you're dealing with, right? So for example, if your data has 1000 columns, you're working with 1000 dimensional data, right? And this 1000 dimensional data could be very resource consuming when you run this, let's say when you run any algorithm on this. So what we do is we try to reduce the number of columns by making components of data, and this is done by absorbing the common variance from the data, right? If you go on understanding this mathematically, each of the uh, the combination of two columns are taken and their common trajectory is made. The points are projected on this common trajectory, and this trajectory is then taken as a new column where I can drop the original two columns, right? This is a little technical as of now, but yes, you learn this again in machine learning. And in this particular process of dimensionality reduction, we use covariance matrix. So their covariance matrix plays a very important role because we are capturing the combined variance from two columns, and we are dropping those two columns and keeping the new one combined variance, right? So this is how it works. It's called principal component analysis, right? PCA in short. You'll learn this in machine learning, right? So these are some of the usage of covariance. All right, so let's get back to the analysis. If you see here in the data tab, the data analysis tab that we have, right? This data analysis tab did also contain covariance and correlation, right? So these two can directly be used. Let's start covariance first, right? It needs input range of data. So what I'll do is I'll simply select all the numerical columns starting with year, right? And we'll go up till the last column of the data, right? And this is the last column of the data, and we'll simply plot the covariance matrix. All right, so not a problem. What we'll do is, I think we are taking the columns as well, right? So we'll take from C2. We'll take from C2 because C1 contains the name of the columns, right? So we'll simply take C2 to, let's say, AG. I think we have the last column to mention the number here. Just give me a moment. Right, so okay, 824 records. So we'll simply mention 824. Let me give it another try. Right, so C2 to 824. Okay, not a problem. What we'll do is we'll take from C to AG, right? And we'll simply tick this option that labels in the first row. So, okay, I think just give me a moment. Yeah, all these are. Right, so I'm okay. I think this is something that is not here. I think this is some wrong value that is present here. So hmm. I think this should go now because it contained letter B, right? Which is why I think it was not able to do it. Okay, I think there is something wrong with the data itself. Give me a moment. I'll use another data. Give me a moment, guys. I'll quickly check the data. All right, so we have this data, right? This is the data. It's very similar data, but here what's the year that we have is from 1000 to 2001 to 2012, right? So let me select the data, format it as a table, right? And then we'll go to our data tab to perform the correlation analysis and the covariance analysis, right? So let's start with correlation. The input data is from A to G. It's not A to G. It should be from C to G. Yeah. Yeah. So we are able to perform correlation analysis on this. This will consume a little time, right? And then a correlation matrix will be displayed. Right. Just to give you this idea, the total columns that we are dealing with is around 40 columns. Right. So this is the output that we have got, and this is the correlation matrix. Right. This is the correlation matrix. If you look at this matrix, right, the size of this matrix, let me show you the complete matrix at once. Right. So this is the size of the matrix. Yeah, this is the size of the matrix. And each of these values represents the respective correlations. Right. And what these correlations are, let's say here the columns are listed out, and here also the columns are listed out, and the relationship is shown on both of these columns, right? So for example, let's say if we want, let me zoom in, all right, and let me show you the correlation values, right? So for example, let's say 0.73. This is the correlation, 0.73. This is the correlation between, let's say, homicide not amounting to murder and kidnap and abduction, right? So this basically says that if the number of kidnapping and abduction cases increases, there is a high chance that the culpable homicide not amounting to murder will also increase, right? Because the relationship here is very high, right? In the similar way, let's say for this particular value, 0.74, it says the correlation between rape and this is kidnapping and abduction, right? So it says that if the number of kidnapping and abduction increases, the total number of rapes are expected to increase across the country, right? This is for the complete country of India, right? So this is how it's released, and this is the real data that is released by NCRB, which is National Crime Records Bureau. They keep record of all the crimes happening in a country across the year. All right, so this is how you can analyze. For example, let's say not this value, let's pick any negative value. Okay, so it seems like we don't have any negative values. All these are positively correlated since these are crimes, different types of crimes. And you must have seen when one type of crime is committed, there are a lot of other crimes, those are associated with it, right? So, for example, kidnapping and murder. These two are different crimes, but there are a few chances where a person who has been kidnapped is murdered, right? So this will show the relationship or the strength of relationship between these two features. This is how the data is analyzed, and you can get a lot of information from this data itself, right? And this is the correlation matrix. If you want, you can highlight this matrix using the conditional formatting, right? I hope everyone knows this. The conditional formatting will highlight all the cells that have maybe values less than 0. Right, all the values, those are less than 0, will highlight it with the red color. So we can see in this matrix, right, all the values, those are highlighted with red. They are less than 1 value, which is negative correlation. And we can see the only negative correlation that we have is with respect to year column, right? So year column, although it's continuous in nature, right? Although it's categorical in nature, but it's represented as a number. Right? You can simply apply a basic logic right? You can simply apply a basic logic. For example, to understand a feature year, right? 2001, 2003, 2004, and so on. Let's say there are 2 years, 2023, right? And let's say 2013, right? So these 2 years, they represent two different years. They are not real numbers, right? This is just a representation of the number of years, right? So here, what happens is if you try to calculate the average of both of these years, right? So I'll simply use the average function, right? I'll pass these two values and I'll get something like this 2017.5. This does not actually represent a year, right? And once the output that you're getting after calculating the mean or any other statistic that is defined for purely, let's say, continuous data, right? If it does not make any sense, you can very well deduce this that this is a categorical column, not a continuous data, right? Year is a categorical column. It is just represented as a number. All right. So this is how you can identify, even if the number is if the column is represented in the form of a number, still you can, based on logic, based on common sense, based on what you have learned through statistics, you can simply come up to a decision and you can directly deny any column being continuous in nature even after it is present in the form of a number, right? So this is how the correlation analysis is done, and the very similar way covariance analysis is done, right? So if we can again go to the complete data analysis sheet, let's do the covariance analysis on the same data that we have selected, right? All right, so I think it's not taking the same data. We are getting it for correlation, but we are not getting this for covariance, right? Not a problem, right? Since this is more reliable and you'll be using correlation matrix everywhere, right? So you can use correlation matrix like this. All right. So yes, guys, I hope everyone is able to follow this, right? The concept was explained so that you understand what these values actually represent. All right. So yes, guys, with this, we are wrapping up the session for today. I hope everyone is able to follow this. Right? Just give me a yes or a no in the chat section if you're able to follow today's session. All right. Great. All right. So I'll share the GitHub link very quickly. Just give me a moment. Right. So this is the GitHub link that I'm sharing with everyone. Right. You'll find on this GitHub link right? So on this GitHub link, you'll be able to find the practice problems, the data set that we are discussing in the live sessions. You can download it directly from there. One data set has to be downloaded from Kaggle. I've uploaded a PDF related to it. Simply make an account on Kaggle and you'll be able to download any data. All right. So guys, don't worry about the formulas. Formulas are something that will be on the tip of your fingers once you start exploring these topics, right? Formulas are not something that you need to sit and learn. It will be on the tip of your fingers, on the tip of your, knowledge as and when you spend more time analyzing the data, as and when you know, get familiar with the statistical approaches we are covering in the live sessions. All right. So, yes, guys, with this note, we'll wrap up the session for today. And thank you, everyone, for joining the session. I wish every one of you a good night.